So where we last left off, we talked about, oh yeah, of course, please make sure you're keeping up with the reading. It's not many pages, but the book is fairly terse in its description, and you will find that you'll need to go off on the internet and find some things to fill in some of that detail. I try to do that in class as well. Okay, so when we last met, we talked about, to jar your memory, this idea of random variables. And we said and a random variable is a function that measures something over what we call the raw event. And so you can consider a raw event, for example, a string, and that was the example we used, of heads and tails from flipping a coin 3 times. And that's what that little omega is. And the function might be something, for example, a function that counts the number of heads that occur in 3 flips of a coin, of a fair coin. And so we talked about this idea of the domain and the range of that function. And so here, the domain omega would be all of the possible outcomes for that raw event. And you call that function and you get some value. And in the case of 3 flips of a fair coin, that value we saw counting the number of heads would be 0, 1, 2, or 3. And so for this random variable, we can have a number, like an integer. We can have a number like a real number, and so forth. It all depends on what the range is for this function. Okay, so we also looked at the distribution for the 3 coin flip, and we saw that we can graph this instead of depicting it in table format. And as a graph, we no longer look at the values, we look at the shape of the graph. And the shape of the graph tells us something about the system over which the random variable was computed. And so we also talked about the idea of constructing complex events, where those complex events might be some combination or union, if you will, of a set of individual outcomes. And in the case of a random variable, we might be concerned for that 3 coin flip counting the number of heads. We might be concerned of the occurrence of 0 heads as well as 1 head. And we use summation to do that. And the summation is a procedure, what we call the CDF, or the cumulative distribution function. And with this CDF, we can take a simple interval, or we can take a complex interval by subtracting the CDF for the 2 upper bounds of interest that frame, if you will, what that interval is. Okay. We also talked about this idea of a marginal distribution. If we have more than one random variable, we get what's called a random vector. And we talked about the procedure of isolating one of these probabilities for one of these outcomes by so-called marginalizing. And we called it marginalizing because we literally sum, in the case of the coin flip, down the margin, or in the case of a die roll, across the margin. And we can arrive upon the probability of a single random variable, even though we get vectors that talk about the probabilities of the co-occurrence of values for that random variable. Okay, so any questions about this? Any questions? No? All right, so to jar your memory. Okay, so let's start with a warm-up, and to do this, I'm going to fire up MATLAB to motivate the next 2 things that we're going to focus on for now, namely expectation and variance. And this expectation and variance talks about high-level descriptions that we have as it pertains to the shape of a distribution. Again, we talked about the shape of a distribution as being descriptive of the underlying system from which you measure this information, or random variable. So let's take a look at this. So suppose we played a game just like the dice game, right? And we're going to simplify it. And this is, we're going to call it the coin game. And in this coin game, you're going to wager $1, and I, or the house, is going to wager $2. So I'm going to flip a coin, and you're going to guess either heads or tails for one of the outcomes of the coin. And how the game goes, if you're correct, you get to keep the house's $2. So your wallet increases by $2. And let's just assume the wallet starts out at 0. And if you lose, the house gets to keep your $1. So one of the questions you might ask is, how much will you win, or how much can you win if you keep playing this game? And you can imagine, this might work albeit in a more complex way with slot machines or any other game, like poker or blackjack or what have you. And so the question is, how much will you win if you keep playing this game? And the house might want to compute this to see how much might they lose, because what you win, they lose if this game proceeds. And in fact, if you were, working in a gaming organization, you'd actually do these sort of calculations to make sure that the wager amounts and the items that you use over which the probabilities are calculated are such that this is profitable for the gaming organization. So let's take a look at this. So half the time, right? Let's say you guessed heads. Just to simplify this, let's say you always guessed heads. Because whether you guess heads or tails is not the point. It's just a matter of which way the probabilities play out and how the wagers play out over time. So let's say, for the sake of assumption, that you always guess heads. That means half the time, probability of heads is 0.5, okay? So that means half the time you're going to win, half the time you're going to be correct. And so that means half the time, or 0.5 of the time, you're going to get the $2 from the house. Okay. The other half of the time, because probability of tails outcome is 0.5, the other half of the time you're going to lose, right? You're going to guess incorrectly. So that means you're going to lose $1. Mathematically, we can note that as being you getting -$1, right? Okay. So that's 0.5 proportion of the time. It's going to be $2. So we can multiply this 0.5 by the $2. And the other half of the time, 0.5, you get -$1. So if we do the calculations, that results in 50 cents, right? And so that is the theoretical, and I stress the idea of theoretical because how probabilities work is that you have to engage with something, quote unquote, enough times for it to resemble what that theoretical construct or theoretical result is. Okay, any questions about this? Make sense before we move on? Okay, great. So let's try this in MATLAB. Right, so I'm going to bring up MATLAB, and we're going to create a little simulation to model this, and we'll just call that the coin flip game. All right, so let me escape, minimize that. So let me bring up MATLAB. And let's create a new script. And let's call this routine, I like to save it first before I write anything, coin, my vision's a little blurry, coin flip test 2019. Okay. All right. So we're going to, some number of times, we need certainly the probability governing a coin's outcomes, and some number of times we're going to play this game. So let's say the probability of a heads outcome, right, as we said, is 0.5. And we're going to use a very simple form of stick breaking in order to simulate this flipping. So now we're going to need a flip outcome. Well, let's call it coin flip, C flip, right? And that's going to equal some number, and that's going to accept the value that results from using the random number generator for the coin flip. And we're going to do this some number of games, right? So let me just say num trials, and let's say we do it 10 times. So 10 many times we're going to play this game, and let's assume for each of those times you play the game, those 10 many times in this example or this juncture, you're going to continue your guesses as heads. And so let's say my guess is equal to heads. Okay. So now we're going to loop for I goes from 1, increasing by 1, incrementing by 1 to num trials. I'm going to go ahead and I'm going to play this game. So coin flip, I'm going to randomly select a number on the real number line between 0 and 1. So I'm going to say rand 1, so it'll give me a single number. And then I'm going to check to see if this coin flip is in that region of the stick associated with the heads event, and that's going to be up to 0.5. So if the coin flip is less than or equal to probability of heads, right? And that would correspond to being on the first piece of the broken stick. Then I'm going to call that heads. Otherwise, I'm going to call that tails outcome. Okay. So now I'm going to have another variable called coin result, right? And coin result is going to be a string that's going to be either heads or tails based on this particular stick breaking implementation. So if that value between 0 and 1 is less than equal to probability of heads, so it's between 0 and 0.5, then I'm going to say coin result is equal to heads. Otherwise, that means it's greater than probability of heads, greater than 0.5, but less than equal to 1. In that other part of the stick, I'm going to say coin result is equal to tails. Okay, so this is my, tails. This is my basic coin flip using stick breaking construction. Any questions about this? Make sense? Okay. So now that I have that some number of times, num trials many times, I'm going to flip this coin. And now I want to implement this wager. So let's say my wallet starts out at 0. And let's say my wager, right? We said I'm going to wager $1. So let's say 1 equals 1. So 1.0 just to be more correct. And then let's say the house wager is equal to $2, $2.0. Okay, so we have the basic plumbing in place. And so what happens, if the coin result is the same as my guess, then I get the house's money. So my wallet increases by the house wager amount. If the coin result is not equal to my guess, then I'm going to lose my wager. So my wallet will decrease by my wager. Okay, so let's do that. So I'm going to do a compare between the coin result and my guess. So I think it's string compare. Let's check help just to verify help. strcmp. So string compare compares two strings and it returns a logical one or true if they're identical. Okay, so I'm going to use string compare. So if strcmp, if the comparison between my guess, and the coin result returns a true, I'm going to increment my wallet. That means I'm correct. I'm going to increment my wallet by the house wager because I'm going to get that house's wager amount. So my wallet, if I guess correctly, is equal to my wallet plus the house wager. Otherwise, my wallet is going to equal my wallet. I'm going to subtract my wager. I'm going to lose that money. Okay, my wager. Okay. Any questions about this so far? That makes sense? Let me see if I can make this a little bit bigger. People can see in the back. Okay, so that's the basic logic of the game. So then over the 10 mini trials, in this case, num trials is 10, I'm going to get some pool of money in my wallet. And now I want to compute the average amount of winnings because I take my total winnings divided by the number of trials I've played. So average winnings is equal to my wallet divided by the number of trials. I might be up on some trials, I might be down on some trials, but the average, if I spread that out over the trials I've played, that should tell me on average how much I've made. So now let me just produce a string message equals sprintf average winnings equals, I'll make it a float and use that string. I'm sorry, yeah, average winnings. Okay, there we go. So now I'm going to display that message. And then I always like to, this is my own habit, display the message done, string done, because I like to be able to have a statement I can set a breakpoint on that's not the code that I'm executing. All right, or not the code I'm interested in. All right, so let me try that out and let's see what happens. So I will clear CLC. All right, and let's try that out. So average winnings is negative 10 cents. So I've lost 10 cents. So let's try it again. Continue. Average winnings. Oh, now I'm up 20 cents. Oh, down 10 cents. Up 80 cents. Well, that's good. 50 cents. All right, that matches theoretically. Question. Ah, I being the player. I should change these variables to player um, and the house. So when I say up, meaning average winnings, I mean the player, the person who's playing, and the house is the one that's conducting the game and doing the flip. Okay. Any other questions? Make sense? Okay. Yeah, it's just when you're talking as the instructor, I have to pretend I'm you, but then sometimes I go back to knowing that I'm me. So it's just, that context switch sometimes gets lost. All right, good. So now let me do something else. So you engage in this run of 10 games and you have some number of winnings. Let's do this a lot of times and see how it plays out over time in order to know how the behavior of this system works over long runs, right? So I'm going to run this as an experiment. And in this experiment, I'm going to iterate through it maybe, 100 times or 30 times. We'll just pick something. So number of experiments, let's just set to, I don't know, 30 times. And I'm going to have another loop for EX gets one going by one up to num experiments. So 30 times I'm going to run this experiment. I'm going to zero out the wallet to zero, and then I'm going to 10 times play this game, assuming that the guess of the player remains fixed at heads, right? You could certainly have the guess change over time. Okay, so let me end that block. End, and I'm going to indent the inner for loop that plays the games 10 many times. So let's see. There we go. Let me indent there so it's a little bit easier to see. So the outer loop iterates over the number of experiments, and the inner loop iterates the 10 many times you play this game. And we saw previously when we did the 10 games, each time we run it, it's a little bit different, right? Question. Ah, just because I want to see over time, you could absolutely, and I hadn't got to that, and that's a good question. You could play the game more than just 10 times, or run the number of experiments. But what I'm trying to look at over a long time is how, if I repeat this 10 game run, how does the number work out relative to the theory of winning 50 cents on average? And so we'll get to that. We'll get to that in a moment. I could do number of experiments as 2, right? Or number of experiments as 100. But what I want to do is I'm going to draw a graph. And to make the graph look interesting, I want to have the number of times I play this game be much bigger than the number of runs in a single instance of the game, because I want the graph to look nice and go across the screen and stuff like that. But you can absolutely tinker with these numbers, and that'll show different things that I haven't gotten to yet for this class. Okay. Any other questions? No? All right. So we're going to plot this average winnings in a single game. And as we saw from the command line, that this changes over time, right? And that's how probabilities work, because it's over a long number of interactions or measurements from your system. You're trying to characterize the behavior, and that's what the distribution tells you. Okay, so what we're going to do is we're going to save all the outcomes of these experiments, and we'll say experiments equals zeros, 1 by num experiments. And this is also to teach you how to do graphing in MATLAB, simple graphs. So we're going to create a vector, and that vector is going to store the average for each one of those experiments. And each one of those experiments is going to be an average over num experiments, many interactions, and num experiments, in this case, happens to be number of trials. I mean, num trials happens to be 10. All right, so I'm going to go down here, and when I compute my average winnings, I'm going to save off that value I get for average winnings. Okay, so experiments 1 comma ex is equal to average winnings. Okay, so I'm going to save that off, and then when I'm done with all my experiments, I'm going to plot which experiments and the value that I stored in experiments. Okay, so num experiments many times. I'm going to play this game. Each time I'm going to save the average winnings, and then when I collect all those average winnings, I'm going to plot them out on the screen. Okay, now let me label this graph. X label num experiment. Oops, experiment meant number. Right, that's the label along the x-axis. The y-axis, I'm going to call that average winnings, and I'm going to give the graph a title. SG equals sprintf average winnings for %d plays, and %d is going to be num trials, right? And I'm going to make that the title message. Okay, so then those pieces is just giving the graph some labeling for the axes, and then I'm also going to set something called a y limit, and that's just going to keep the scale the same, so that when you draw the graph multiple times, you can make comparisons. MATLAB is trying to be friendly in its default behavior. When you plot a graph, it resizes the scale on the axes in order to make the graph look big and look nice. But sometimes you don't want it to do that. So we'll just say ylim, the minimum is going to be, let's call it -5, and the maximum is going to be +5. Okay. All right, so that's just a little bit of bookkeeping. So let's run this and see how it plays out. Okay. Any questions? All right. So we'll start out and we'll run our experiments. We'll play this game, and it's interacting with the coin flip game 10 times. We collect the average, and we do that some number of times and plot. So let's run this. All right, so we do that, and you can see average winnings. It plays out, quite a few times, right? Sometimes it's higher, sometimes it's lower. And so let's plot the graph. Did I misspell that? Yes, experiments. All right, let's try that again. Save. All right, so let me just remove the breakpoint and run it. There we go. So there's our graph. Let me make this a little bit bigger so we can see, and it's hard to see the font in the back. The horizontal axis has the experimental run. We had that set to 100. And the vertical axis has the average number of winnings in dollars. So you can see from one experimental run to the next, sometimes we're up high, sometimes we're down low, sometimes it's negative. Okay. Any questions about this? Make sense? Okay, so to your question, let's go ahead and tinker with some of these numbers. Let's go ahead and change the number of trials. Instead of saying 10 times, let's make it 5 times as many, so 5. So we're going to play this coin flip game 50 times and take the average winnings over that coin flip game, and we're going to perform that experiment 100 times. So let's see what happens. Well, it's the same scale, and that's why I set the scale, but you'll notice here the amount at which it's up and down, it changed. It's not as dramatic swinging up and swinging down from one experiment to the next. Let me leave that graph up and let me just rerun this a few times and actually show you that it does, in fact, um, change over time. Let me do this. I'll put the graph over here and make that a little bit bigger. Okay, so let me run it. And you'll see, yes, it does change, right? It is some stochastic phenomenon. It's never the same each time, but you'll notice here that it does change. If I had num of trials instead of 50, let's say I went down to 5, right? Let's see what happens. When we do that, you'll see it jumps a lot more and swings up and down more over that span of 100 experiments, right? If we change num trials something really high, 100, right? It's much smaller. And if we continue to change it, let's say if we did 500, you'll find that it's even smaller. And so one of the things that's really important to note that as we change num trials to be bigger and bigger, let's say I made it 2,000. So 2,000 times I'm going to play this game, take the average number of winnings, and I do that in 100 experiments, you see it eventually flattens out over time, right? And so that's to drive home 2 points, that when you're dealing with stochastic phenomena, it's never the same twice, and it's really important to be able to characterize the behavior of your system, which is why looking at a distribution is a really important thing. Okay, and so you'll notice here, like if we were to characterize this system, well, we kind of have what looks like an average. If you were to take 50 cents on this graph, let me blow this graph up to make it a little bit bigger. Let me change the limits on this graph to be a little bit tighter. So let me make it from -2 to +2 for the y limit, right? -2 to +2. Save. And so let me go back to number of trials and let me run that, right? So you notice here, if we were to kind of compute a straight line average of all these experiments, that straight line average would be right at 50 cents, right? So we have this idea of kind of the center about which all of the amount of money that you're up over time, the center of that set of values, right? They're kind of above and below 50. 50 is kind of the center line, right? The average. And that coincides, that average, exactly with what we computed theoretically. But for each individual engagement in this game, that 50 many times, or num trials many times, sometimes you're up, right? Sometimes you're down. So here it's 68 cents. For this experiment, it's negative, oh, it's 0.2 cents. Here it's 0.74. Here it's 1.1. So you're kind of, going up or down, and you'll notice that if I change num trials, let's say num trials is 5, the smaller the number of times you engage with it, the more it swings up and down, right? If I only engage with it 5 times, it swings up and down. If I only engage with it 1 time, well, let me change the limits because it's going to exceed the limits on my graph. Let's say -5 and +5, right? Save. If I only engage with it 1 time, well, it's going to be pretty jagged. Where did I lost that. That's 5. Let me run that again. So that's 5. Let me change it to 1. Save. Run that. It's really bad, right? If I change it up to be higher, back to 50, right, you'll see that it's swings much less above and below that 50 cents ideal, right? So we have this idea of the behaviors of the system, and without looking at the individual values, sort of visually you can see that one system behaves more wildly, right? The values swing up and swing down from one interaction with this game to the next. But the center value, this 50 cents, is roughly what the average is that everything is centered about, right? And so this is just to drive home the idea. First, any questions about this? and I'll certainly post this on the among the lecture slides. This is just to drive home the idea that, oops, wrong one. This is just to drive home the idea that a course level description of the shape of the graph governing a system is really, really important to telling you how this system behaves. So if you saw such a system and you saw it swings very wildly, that means if you're going to play it for a small number of times, you're going to really lose some money, right? But if you see a system that varies not as widely, gosh, it's a little bit more stable and you can count on that. So this would be the case if it was wagering, or maybe it's tracking something, right? You're more likely to lose the track versus have a stable tracking on something. So both the average value and how much a value varies above and below its average describes how stochasticity behaves for this system and, moreover, many systems. So let's talk about this average value, this center, right? And talk about this variability, and we'll talk about two quantities, expectation and variance. And what we computed when we computed this 50 cents ideal, we computed the expectation. How much money can you expect, or on average, how much money can you will you get, right? How much money can you expect to make for this example? So let's take a look. Uh-oh, there we go. At expectation. So in the real world, of course, you have multiple descriptors. In the computer vision domain, you have color, texture, shape. And we talked about this idea of vectors of random variables that describe these complex things that have multiple measurements that you might make over them. And so in practice, often it's too complicated. There's too much information, too many moving parts for you to write out a complete accounting of how it behaves. So the only solution is to have a summary, right? And the expectation or center is one summary, or what does everything vary around, and the spread above and below, or less than, greater than, around that center is also another nice summary for how a system behaves. And so this behavior is important so that whoever reads this description can have a rough sense of how the system behaves without having to go into all these gory details, all these moving parts, especially when you have a lot of random variables in a vector. Okay. Any questions about this? Make sense? Okay. So these are so-called summary statistics because they summarize the shape of the distribution, right? And there's more than just these two summary statistics, but this semester we'll only focus on these two. And in data analytics, we talk about a whole host of other things. Okay. So expectation, as in what do you expect to happen or what will happen, quote unquote, on average. And this on average changes or can change depending on how many measurements you have. Okay, so this is defined, our expectation, as a so-called probabilistic average. And so if your distribution is uniform, and I'll explain what that means in a moment, but the expression for expectation, oftentimes with these quantities you calculate, you substitute a symbol to represent the result of computing this thing. And so Greek letter mu is the mean, and the mean is nothing more than the probabilistic average. And how you'd write it functionally is E of x. E stands for expectation of, where big X is the random variable. So mu, the mean, is the expectation of a random variable big X. Now you could substitute big Y or whatever variable is the topic of conversation. And so what that expectation is, you take the value, each of the values X, right? And then you multiply, that's where the weighted part of the weighted sum comes in. You multiply by the probability that random variable X returns value little x. So in the case of that coin flip game, well, you had two values. You either had $2 or you had minus $1. The probability of getting $2 was 50%, 0.5, and the probability of getting $1 was losing $1 is 50% at 0.5. So literally what we did is we computed the expectation in that case, right? Now, another way of computing expectation, sometimes you just have data and you don't know at all what the true probability is. In that particular case, what you do is you make the assumption that each outcome is equally likely. If you have n many outcomes, well, the probability of each one is 1 over n, right? And so what you're doing literally when you take the average, what you're doing is you're computing an expectation. You have each of your values, x, and then you have the probability of each of them, which is 1 over n. If we calculate that, that's the sum, x, times its probability 1 over n, right? If you add them together, that's exactly this quantity, which is the average. So the average is just an expectation with an assumption that you're making on the probability of each of the items. You're making the simplifying assumption that each of those items, those values that you observe, have an equal probability. If you do know what the true probability is, then absolutely use it. But there's a solution in place by just substituting the average, and that works, works pretty well many of the times. Okay. Any questions about this? That makes sense? Yes? Okay. So dispersion, the spread. And so this variance quantity measures how the random values that you observe are spread out around the center, where the expectation is our center. We saw that the average value was 50 cents theoretically, and we saw that on some runs of this coin flip game, you'd be greater than 50 cents. Sometimes you'd be less than 50 cents. But nonetheless, over time, right, we converge if we have enough measurements down to this 50 cents. And so in some cases we saw when the number of trials for which we played this game was small, right, it swung much higher and much lower around that center value. When the number of trials was large, we saw that we swung above and below this 50 cents. It varied less widely. And so this idea of variance will tell you about a distribution that if you're trying to guess a value or estimate something, it's more easy to get it wrong if something is more widely variable, right? And that's why when we had those two versions of the coin flip game, we saw that the first version where we had, I think it was 0, 1, 2, 3, and we had 1/8, and we had 3/8, and we had something like this. That varies a lot less than the fictitious version where it was just 2/8 for each value, right? When you vary more widely, it's easier to get your guess wrong. So variance is a really important quantity in describing the behavior of a system. Okay. Any questions about this? No? All right. This varies less, so less. Then this varies more because there's more probability mass distributed over all of the values. Okay. Any other questions? So, all right, I forgot this was here. And so the question about which one would you bet on, right? You'd rather bet on system X than system Y because it's easier to get it right for X. It's harder to get it right for Y. Because they're equiprobable, if you play the game for a few rounds, you'd notice, oh, wait a minute. Well, the 1 and the 2 seem to pop up or appear 3 times as much as the 0 and the 3, right? It does not vary as widely. Whereas in the Y version of the 3-coin flip game, each of those values pop up an equal amount of time, okay? And so the reason why you would rather play, or you're more likely, or it's better to play System X for the 3-coin flip game, is because it doesn't vary as widely in the values. Okay? All right. Questions? Okay. So variance. Variance is the amount by which a random variable's value spreads out. If you have something that's low variance, that means it's easier to predict the outcome. If you have something that's higher variance, it's harder to predict the outcome. It has more what's called dispersed probability mass. So how do you define the spread out, right? Spread out with respect to what? Well, with respect to the center. And the center of a distribution, often called its location, is the mean, which you compute by the expectation, which you could also compute as the average. Okay, so the variance is not just any average, it's a probabilistic average, and it's the average amount of dispersion or difference between a random variable's outcome and its center. Now, in this value, or this expression, we have sigma squared is the symbol for variance, and as a function, you'd say variance of that variable x, and it's the expectation of the variable x minus its center. The center is e of x, and we square it because we're concerned about the magnitude but not the direction. We don't really care for variance whether it's smaller than the center or larger than the center. In the case of the MATLAB example, is it below 0.5, 50 cents, or above 50 cents? We don't care if it's above or below. What we care about is the distance, the magnitude above and below. And so we square this difference between x and its expectation because we care about the magnitude and not the direction. And so if we do this in a discrete system, right, where we have a countable number of values or outputs of the random variable we can observe, we take the values x we observe minus mu, where mu is the result of computing the expectation. We square that difference, and then we multiply that by the probability. Again, if you don't know the probability, you can treat each of these outcomes as equal probability and use 1 over n. Okay? So it really is the average amount of difference between the variable's outcome and its center, which is the expectation. Okay. Any questions about this? Make sense? Okay. So the random variable outcome is x, its mean, mu, and then you care about the difference and not the direction, so you square. But the variance has a square term in it. And it's kind of hard sometimes to talk about square terms when we're dealing in real units, right? So suppose you're talking about variability in temperature. Variance would say, oh, 9 degrees squared. Well, what does degree squared mean, right? Well, certainly it's respecting the math, because if you have something degrees times degrees, you get degrees squared. But it's hard to interpret that. And so if you're dealing something with dollars, like let's say the change in a share price on the stock market, how much does it vary over time? What is the average share price, and how much did it flicker up and down in its price? Well, dollar squared. Oh, how much did it vary? $8 squared. What does that mean, right? And so because of this squared term, yes, it is a valid description for the variability. It's hard to compare that amount of variability to the actual central value. So if you said on average 50 cents plus or, and it varies, 70 cents squared, right? Well, what does that really mean? So we need a way to be able to talk about this variability in the same units as the center, so you kind of know how far off from the center you are. Okay? And so this is where something called the standard deviation comes in. The standard deviation is a kind of fix-up. We talked about there being a lot of fix-up in mathematics. And this particular fix-up says, you know what? This squared term, it kind of messes up my units, and I can't really compare dollars squared to dollars. If my average is dollars, I want to know how far I am off in dollars. So I'm going to take the square root of this variance, and that square root of the variance is called standard deviation. So because variance was called sigma squared, right, lowercase sigma, Greek symbol, the square root of that is called sigma, and sigma is standard deviation, lowercase sigma. So functionally, it would be sigma is equal to STD of x, standard deviation of x, which is nothing more than the square root of the variance of x. Okay. Any questions about this? Make sense? Okay. And fortunately, in MATLAB, there are functions that will do this for you, but you're perfectly capable of calculating these yourself. You compute the expectation of a quantity, you subtract that quantity, each measurement from its expectation, and you square those differences, multiply by the probability. Okay. All right. So when you have a standard deviation, this is just a canonical distribution. It's not the distribution for any particular system. I just drew it to show a distribution. And we have the center, mu, and you can see, gosh, it kind of looks in the middle. If you were to take the area under the curve from minus infinity up to mu, this shaded region, that would be 0.5, right? It's a probability distribution, and all probabilities add to 1 if you take the probabilities over every possible observation. And the mean is that point that represents half of the probability if you were to sum that together with a CDF. And this variance, or standard deviation, and the mean are often called the location scale parameters of your distribution. The mean mu tells you where it's located. If mu were bigger, our distribution would be moved over someplace. Let's call that mu prime, right? That tells you where this distribution is located. Where is the central value, or what is the central value about which all the other values vary, right? And the scale parameter, or variance, the square root of it being the standard deviation, just tells you how wide it is, how dispersed. So if we took the same distribution, and let's say we had another one that was a little wider, it had more probability mass over different, more values in the domain, that would correspond to a sigma, a standard deviation, which was bigger. Now, it just so happens that in something called hypothesis testing, you can use the relationship between your center value mu and your standard deviation to test membership within a system. And what I mean by test membership in a system is you can say, okay, well, I have a stochastic quantity, and the distribution tells me how those quantities arise and thus describe the behavior. If I make a new observation, how likely is it that this observation came from the same source that produced this distribution? And that's used in things like spam filters, right? A spam filter has distribution that talks about words, occurrences that are in legitimate emails. And you get a new email, and you check to see how likely is it for that new email's text to come from all of the legitimate emails that you get. And if it is not likely to come from it, it doesn't have membership in that distribution, then you say, that's not typical, it must be spam. But sometimes these spam filters are wrong, right? You can go into your spam box, you can correct in Gmail, go into your spam box, you see an email that characterizes spam, you click on it and say, nope, let me correct it. What it's doing there is recalculating that distribution of what normal email looks like, okay? Now, there's a relationship between the location and scale parameter. If you have plus or minus 1.96 times the standard deviation above and below this mu, all of that region represents 95% of the probability. So what does that mean? That means if you're trying to determine membership, and in the statistics community, 95% is assumed to be assured. So with 95% likelihood, or confidence as it's called, a particular value or email belongs to a distribution, it's within that distribution, then you can characterize it as being from the same system, right? So that's how hypothesis testing works, and we'll talk about that a little bit later in the semester, and that's how spam filters work, with a little bit more machinery on how you represent words as distributions. Okay. Any questions about this? Yeah, make sense? So we can use this idea of high-level descriptors, so-called summary statistics, to describe the shape of the distribution. And in doing so, we no longer have to deal with the individual details of all the individual probabilities that collectively define the distribution. Okay? All right. And so we talked about this idea of multiple measurements. And when you have a random vector, we motivated that with some pictures. And, you know, if you consider apples, right, pictures of apples, what defines an apple from something that's not an apple is a co-occurrence of different measurements. You can have color, right? So here we see some reds, some yellows, some greens, and it's not just any red, yellow, and green. It's certain types of red, yellows, and green, and they occur together. Likewise, you have certain shape, right? It's kind of roundish, right? And it kind of comes into a dimple on the top and the bottom. Some are longer, more oblong, bless you. Some are more round, like a baseball, right? But nonetheless, you have some measurements, color, texture, shape, in the case of visual objects, and they occur together. And certain colors, textures, and shapes that occur together define apples, right? You don't see an apple that's shaped like a banana, right? You just don't. You don't see a purple apple, at least not yet. Maybe genetic engineering, someone will make one for whatever reason, but you don't see them, Okay. And so you have these coupled measurements, and it's important to measure this idea of what that coupling is. That's another characterization of your distribution. So not only do we have a certain color red and a certain shape and a certain texture occur together to define an apple, well, if they occur together, that means there's some coupling. And if you can describe the coupling, then you can determine what appleness means or what grapefruitness means or what have you from images. And so when we get a random vector, which is typically the case dealing with this in the real world, often it's important to depict or measure rather what the coupling is, not just the dispersion, the variance, and the center. So enter this new measurement called covariance. And covariance takes the spread between each measurement and its center, and it multiplies them together. Now, for covariance, in this case, we're looking just at the two variable covariance. There is covariance for entire random vectors for more than two, but we're not going to talk about that today. So we have the covariance between two random variables, x and y, and that's the expectation. So it is whatever quantities in the open and closed curly brace times the probability, right? So we have the expectation of x, random variable x minus its center, and we multiply that with the difference between y, random variable y, minus its center. So we're multiplying together the spread between x and its center with the spread between y and its center. And that's called covariance. Mathematically, of course, we're going to have some sums. We have to sum along the x's and the y's, and there's the measurement x minus its center. There's the measurement y minus the center, and we're going to multiply. Now, in this case, you'll notice these differences. These quantities, you can multiply a positive by a positive by a negative, or a negative by a negative. So covariance, therefore, you notice there's no square term. So we can have a positive covariance or a negative covariance. So we take the quantities here, we multiply them, and then we multiply it by a weighted sum, a weight being the joint probability. That's the probability of the two vector in this case. Okay. Any questions about this? Make sense? So let's ground this out in a graph. Now, on the left-hand side, your left, we have a graph on the horizontal axis. It talks about economic growth. So, jobs are doing well, and a lot of people are working. Salary increases happen, and people go out and they buy more stuff. They go on vacation and so forth. Because of that, well, businesses need to increase output, right? They buy more raw materials, they produce more products, so they can sell more. Now, that results in the company being valued more because their revenue increases and their profit increases. And if you're a publicly traded company, that translates to your stock price going up, your share price. Apple sells more iPhones, their share price goes up. Apple sells less iPhones, their share price goes down. So on the horizontal axis, we see economic growth, and that's typically described as a percentage increase. Apple stock went up 0.5% last month, right? They might explain it like that. If you watch CNBC or any other business channel, they'll talk about stuff like that. On the vertical axis, we have stock market returns, the amount of money or increase that you had. So you'll notice here, if we take an individual point, we had a certain amount of economic growth, and we had a commensurate stock market return. Now, let's call one variable x. So this is x variable we're measuring, and the y variable here is y. And so you notice here, if we take all these points and we go from one point, this first point, to the next point, for some unit step increase along x, we have a commensurate step increase in y, right? It's kind of sloping upward. And as you can see, that trend, for the most part, is the case if you go from one point to its right-hand neighbor, right? If you were to fit a single line that kind of connoted or described the average of these, you'd have a line that was upwardly sloping. That's what a positive covariance is. A positive covariance says a unit step increase in one quantity, one measurement, comes along with a step increase in another. And the size of the covariance translates to the steepness of the slope of that line. Okay? They vary together. They co-vary. Likewise, on the graph, or for the graph on the right-hand side, we have another system. On the horizontal axis, we have world oil production, and the units there would be barrels of oil. And on the vertical axis here, we have gasoline prices. And simple supply and demand says that if you have more oil, well, gasoline is derived from oil. If you have more oil supply, the cost of gas goes down, right? Similar for like apples. If you have more apples, a bumper crop of apples, the cost of apples goes down. Supply and demand. There's more of it. They want to sell them, so they lower the price. So here we have a negative covariance. You notice if we were to fit a single line among all these points, it would be a downward slope. If we take any point here, right, some unit step increase along the x direction is commensurate with a unit step decrease in the y direction, right? And that's what a negative covariance looks like. And it kind of makes sense. If there's more production, the price goes down, okay? So we have positive covariance on the left-hand side for the graph, and we have negative covariance for the right-hand side. Any questions about this? Yes. I just said best fit more loosely. We can actually talk about regression lines at another time. But for now, you can think of it as a unit step increase in one or unit step decrease in the other. And this line, for now, you can just imagine taking the average value as you go along. And I'll just say it that way for now. But it's actually a regression line, but we're not ready yet this semester to talk about that. Okay? All right. Any other questions? No? Make sense? Okay. So this is our covariance. But there's a problem with covariance, right? And we're going to fix this up in a slide or two. So if you have a covariance, you're multiplying one quantity by another. So you're going to have a number, like you could say a covariance of 123.45 or covariance of 34.7. But it's useful to be able to express them on a percentage scale because the units are confounding. So let's say you had economic growth versus stock market return. Well, one variable, economic growth, would be percentage increase. Well, Apple had a 0.5% increase in iPhone sales. Oh, that's the economic growth. And on the other, the stock price increased by $2. Okay, wonderful. So if you're looking at the covariance, you'd have percentage increase times dollars. What does that unit mean? It's not really meaningful. Likewise, for oil production and gas prices, that graph on the right, you'd have barrels times dollars, barrel dollars. Okay, what's the covariance for this oil gas price thing? Oh, it's 20 barrel dollars. I was like, what? What's a barrel dollar? Okay, so it's important when you're talking about the coupling to be able to talk about them on something that looks like a percentage scale. And that's where something called correlation comes in. You want to look at the total spread contributed by the coupling between one variable and another, because variables have a dispersion or a spread, right? What of that spread is due to the coupling with another variable. So that's what correlation is. Correlation is marked by described by Greek letter rho, right? And it's the so-called normalized or percentage scale expression of linkage. And so to compute correlation, we take the covariance between those two coupled variables and we divide them by two things, the dispersion or the standard deviation of the first one and the standard deviation of the second one. And you can think about it as kind of canceling out units, and now it's on a percentage scale, right? Which is kind of cool. And correlation varies between two values. Perfect correlation has a value of +1, and perfect negative correlation has a value of -1, right? And what does perfect correlation look like? It looks like a 45-degree angle. For one unit step in one variable, you have the same amount increase in the other variable, which would correspond to a 45-degree line. Okay? So $1 increase in one, or 1 percentage point increase in economic growth would be $1 increase in market value. Likewise, we have negative correlation. In this case, one unit decrease in one variable is the same amount unit decrease in the other variable. And so this normalizing by dividing the covariance by the standard deviation of the variables involved gives you this correlation. Okay? So you could take a data set and you could tell me, for two stock, what is the correlation? Now, For securities, it's a little bit different because this is a so-called linear function, and stock market prices are non-linear. There's a whole host of stuff involved, but you could at least say, gosh, are these things related, right? And so, you could try something obvious like oil versus gas. You could take, computer chip prices, computer chip company stock versus computer company stock, right? Because computers use chips. So there's lots and lots of correlations, and people do use it to try to gain information on what the coupling is between various measurements. Okay, so let's end there, and I will see you all on Thursday.